So guidelines for estimating behavioral states. So I have a set of 5 questions you should be considering when deciding which method to use. First, what are your research objectives? What are you ultimately trying to get from estimating behavioral states? Most of the time, it's probably just an intermediate step you need to reach before your final goal, but these should be considered when trying to decide which method to use. 2, do your tags report sizable location errors? If you're using GPS, you can probably get away with doing things that you can't get away with for Argos tags. 3, how frequently are your tags transmitting? So if you have tags that transmit every 5 minutes or multiple times a second, you can potentially do certain things you can't do if your tags transmit every 6 hours. Also, are you trying to estimate more than 2 states? A lot of models are fine just estimating 2 states on their own, but then might have trouble with estimating more than 2 states. So that's something to consider. And then, are you interested in fine or coarse scale behavioral patterns? So with the data sets we evaluated, if all we're interested in is maybe like the initial breeding phase and then a migratory phase and then a foraging ground phase, then it seemed that our data worked better for estimating those when they were much coarser. It's like an 8-hour time interval. But if we left it at the original, maybe hour time interval, it would have had a more difficult time potentially identifying these. So the process, the ecological process you're interested in should also be considered when deciding how you're going to analyze your data. So first, for your research objectives, often, again, the behavioral state serves as an intermediate step for subsequent analyses. So maybe identifying foraging grounds or movement corridors. You can use any of the different models I showed if that's your kind of your goals there. If you're investigating the effects of environmental covariates on state transitions, maybe state-space models or certain forms of them, or HMM, hidden Markov models might be more appropriate compared to the non-parametric Bayesian model. And if you're estimating and characterizing states from numerous data streams, the hidden Markov model or the Bayesian models might be more appropriate for that. And estimating these behavioral state habitat associations, you often want discrete or finite states. So therefore, hidden Markov models or the M3 and M4 methods might be better than state-space models. 2, do the tags report sizable location error? So for marine animals, typically tracked with Argos, oftentimes have large errors greater than 1.5 kilometers. So essentially, you're going to need some form of state-space model, whereas for terrestrial animals with GPS, or if you're using fast-lock GPS for marine animals, errors are often much slower, typically around 30 meters. So it's essentially negligible in that case. So animals tracked with Argos using Doppler shift, you need a state-space model at the very least to account for the error if you're not going to estimate behavioral states with it. But alternatively, yeah, again, you could fit hidden Markov models or M3 and M4 as long as first you process and account for the location error with a state-space model beforehand. Animals that are tracked with some form of GPS, you could use essentially any of these methods. Although the state-space models that I've shown tend to be more appropriate or have more things going on to help with Argos tags themselves. 3, how frequently are the tags transmitting? So regarding either data set size as well as the time intervals, whether it's regular or irregular. So if the time intervals are highly irregular, you probably want to use the M3 or M4 model because it's not as reliant on using discrete time or continuous time. It just is the numeric index of your track or your time series. Alternatively, you can use a continuous time form of a state-space model or hidden Markov model. If time intervals are regular, any of the models I presented on should work fine. If observations are transmitted very frequently, so this is not like a hard and fast rule, but let's say it's more frequent than 5 times per minute or 5-minute time intervals. State-space models or the non-parametric Bayesian models might work better because there are some components of hidden Markov models where pretty high autocorrelation isn't necessarily accounted for well. So unless you're using maybe like a hidden semi-Markov model or maybe a continuous time form, it may not identify these states that well. So yeah, hidden semi-Markov models is another option. 4, if you're trying to estimate more than 2 states, this could be also impacted by the number of data streams and the differences between these possible states. So the hidden Markov models or the M3 and M4 methods are typically better for doing so, especially because they estimate discrete states instead of a continuum between 2 different possibilities potentially. But if you're using a move persistence model for state-space models, you might be able to, estimate behavioral states. But unlike BSAM, where it's assumed to either be in one of 2 states, for what's used in foie gras or that MPMM package, the move persistence model package, it assumes there's a continuum of different behaviors. So there's no way to really identify what it's doing. It's just somewhere along that range of slow and tortuous to fast and straight movements. So it makes it a little harder to nail down. And then lastly, if you're interested in fine versus coarse scale patterns, again, depends on the time intervals and the underlying movement patterns for that given species. So if it's fine scale, state-space models, hidden Markov models, or the M3 method more specifically are probably better compared to the M4 method that might miss these changes. Whereas for coarse scale patterns, I would argue that the M4 method is the best because it's estimating full track segments of relatively homogeneous behavior, whereas state-space models and hidden Markov models rely only on this Markov property that it's impacted by only the previous observation. Although you can use them for this process depending on the time step. So if you coarsen the time step, it'll work fine with these other methods. So other methods that were not covered by today, but that account for Argos location error include a continuous time correlated random walk state-space model and the crawl package, which can be useful, but does not estimate behavior at all. If you want to estimate latent behavioral states, like I've mentioned throughout this presentation, you can use the BSAM package, but that's an older package and works much more slowly. So I suggest staying with foie gras if possible. You can also try fitting hidden Markov models with the HMM-TMB package, which is quite new. And then you can do segmentation and clustering using the SegClust2D package. But that package does appear to get overwhelmed if you have very large data sets. And then some useful resources. So links to different package websites and tutorials are available on the useful resources page for the website associated for this workshop. And that is it.